Welcome to today's deep dive. We are setting out on a very specific mission for you today.
Yeah, a really exciting one, honestly.
Right, we are unpacking this massive technological shift, like moving from AI systems that just, patiently wait for our commands
Huh.
to autonomous intelligence that just lives persistently in the background.
Always on, always watching, basically.
Exactly. And to guide this exploration, we're pulling from a really fascinating stack of sources. We have an April 4th, 2026 Substack post.
Right, by a developer named Shish.
Yeah, it's titled Claws, Curiosity, and a Raspberry Pi.
Yeah.
And we're looking at that alongside the official developer documentation for the Openclaw platform.
Which is super detailed, by the way.
Oh, totally.
Yeah.
Now, we did actually try to pull the original Andrzej Karpathy tweet that sort of sparked this entire architectural movement, but our system's privacy extensions actually blocked the x.com link in our source pool.
Yeah, that happens all the time with those extensions.
Right. But fortunately, Shish's post captures the technical and philosophical essence we need perfectly.
It really does. The mechanics Shish outlines offer this perfect window into how you can construct this kind of autonomous, always-on intelligence layer.
And doing it using really constrained hardware, which is the hook here. We're going to look at how to build this using a cheap, pocket-sized $60 computer.
Right, and why this represents the future of how systems operate.
Okay, let's unpack this. Because think about how we typically interact with technology right now. It basically operates like a vending machine.
Right. You put your money in, press a button.
Exactly. You walk up, you input your prompt, and you wait. A few seconds later, your output drops out, and the machine just goes completely dormant.
It's entirely oblivious to the room around it until the next user approaches.
Yeah. But this new paradigm, it swaps out the vending machine for an attentive thermostat, a system that doesn't require a prompt at all.
It just constantly senses the temperature, observes when a window opens, and quietly adjusts the environment.
Always sensing, always observing.
Yeah, and that transition moving away from a transactional webhook-driven architecture toward a persistent, observant ecosystem. That is the defining frontier in software design today.
And that gets us to Karpathy's concept of claws, which Shish explores in the post.
Right, because a claw isn't just a task-based agent you ping for a response.
No, it's an entity that runs continuous state loops, right? It observes changes in its environment, and it takes autonomous action based on context rather than waiting for a direct instruction.
Exactly. If we connect this to the bigger picture, biological intelligence operates on continuous observation.
Oh, that's a great point.
Right. Like, we don't power down our sensory organs and just wait for an external prompt to notice our surroundings. Observation is a constant baseline for us.
And Shish recognizes that.
Yeah.
If you are building an intelligence layer to monitor, say, an ongoing supply chain or a live network, the software architecture has to mimic the continuous flow of that environment.
Because real environments don't pause. Retail stores, shipping ports, server farms, they are in continuous flux.
All right, they don't stop between operations. So a claw provides embedded awareness.
Yeah, it's the difference between asking a system for a static snapshot of your inventory versus having a system that constantly feels the inventory moving.
And independently reroutes shipments when it spots an anomaly.
Exactly.
So bringing this from theory into practice, Shish decided to actually build one of these claws using the Openclaw framework.
Which is where the hardware choice gets really pragmatic.
Yeah, because rather than running this on some, beefy workstation, Shish deployed it on a Raspberry Pi 5.
Which makes sense. Running a persistent, always-on process on your primary machine is just a recipe for conflict.
Right, because when a developer closes their laptop to commute, that localized persistent AI just goes offline.
Exactly. It completely breaks the continuous observation loop.
Mm.
And furthermore, running local background processes competes for system resources.
It drains your battery, impacts your primary workflows, all of that.
Yeah, so isolating the claw on a dedicated low-cost board keeps it off the main corporate network and enforces these really strict resource constraints.
Wait, aren't Raspberry Pis incredibly underpowered for modern AI? How is a tiny credit card-sized board running advanced intelligence?
Well, I know it sounds counterintuitive, but the secret lies in the architecture that's detailed in the Openclaw documentation.
Okay, how so?
The Raspberry Pi isn't actually functioning as the neural compute engine. It is deployed strictly as a localized gateway.
Oh, I see. So the heavy lifting, like the actual inference, that still occurs via API calls to cloud models.
Exactly. The Pi acts as the physical anchor. It manages the local sensors, maintains those persistent Node.js event loops we talked about, caches local state, and handles shuttling data to and from the cloud asynchronously.
Wow. So by offloading the inference, a Pi running a 64-bit OS with, just 2 gigabytes of RAM is more than capable of handling the gateway workload.
Yeah, the docs specifically say the Raspberry Pi OS Lite, 64-bit with 2 gigs of RAM, handles it perfectly.
It's basically the sensory organ and the nervous system, but it outsources the heavy cognitive processing to the brain in the cloud.
That's a perfect way to put it.
That makes perfect sense. So to deploy this, Sheesh went with a standard headless setup, no monitor attached.
Right.
And reading through the post, the evolution of the tooling here is striking.
Yeah.
Because historically, configuring a headless Pi was incredibly brittle.
Oh, a total nightmare.
Right. You'd flash the OS, then you'd have to carefully inject these wpsupplicant.conf files into the boot partition.
Just to get it onto the network.
Yeah, just hoping the syntax was flawless on the first boot.
But the modern Raspberry Pi imager fundamentally shifts that workflow.
It really does.
Now, the developer pre-configures the target environment directly within the imaging utility before flashing the media.
So you set the host name, Wi-Fi credentials, user permissions, SSH keys, all in the imager.
Exactly. And Shish noted that the device booted, joined the network, and accepted an SSH connection from their laptop on the very first attempt.
That is huge. But wait, earlier you emphasized that working with hardware constraints forces a certain discipline, which is highly beneficial.
Right.
If the ecosystem has removed all the friction from the setup phase, doesn't that inherently reduce the rigor required to build on these devices?
Well, what's fascinating here is the distinction between hardware constraints and setup friction. They aren't the same thing.
Okay, explain that.
Compute constraints force a developer to write highly optimized, efficient code. That is a productive challenge.
Right, that makes the software better.
But setup friction like wrestling with networking configuration files on a headless boot is totally unproductive. It drains creative momentum.
I get it. So when the barrier to provisioning a device is eliminated, developers are far more likely to deploy experimental physical hardware rather than just defaulting to a virtual machine.
Exactly. Preserving that creative energy for the actual software implementation is key.
And once Shish established that SSH access, the focus shifted to deploying the Openclaw stack on Linux.
Which is where things get a bit tricky.
Yeah, the documentation specifies you need a Node.js 24 environment, and you have to verify the CLI tools.
And configure the background system services to actually maintain those continuous loops.
Right, and transitioning from an accessible OS boot into the intricacies of Linux service management introduces its own unique hurdles.
Oh, definitely. Setting up the gateway service involves really precise environment mapping.
And Sheesh actually used an AI copilot like Microsoft Copilot to navigate that, which I just appreciate the honesty there.
Yeah, having a secondary system to bounce command line errors off of drastically changes the debugging cadence for modern developers.
Sheesh detailed a very specific struggle with path configurations and system behavior.
Which is a notoriously frustrating edge case.
Right, like a user might run an interactive shell, type a command, and everything executes perfectly.
Yep.
But the moment they log out or attempt to invoke that same application as a background service via SSH, it just fails entirely.
Because an interactive shell loads a specific set of environment variables that a non-interactive SSH session or a background system service completely bypasses.
Well, that makes sense.
And furthermore, a user-level service often terminates when the user session ends, unless you explicitly enable features like process lingering.
So using a copilot to parse whether an execution failure is due to a missing dependency or an improper path export or a system permission mismatch, that allows the developer to isolate the architecture of the Openclaw gateway much faster.
Exactly. It's a huge time saver. Also, if the Pi has 2 gigs or less of RAM, adding swap memory is critical here. The docs are very clear on that.
Right. And we also see the unique constraints of headless deployment reflected in Openclaw's onboarding protocol.
Yeah, this part is really interesting.
The documentation mandates the use of static API keys for authentication. Because if you try to use a standard OAuth flow...
The system attempts to open a local browser window to prompt for user approval.
Right. And on a machine with no display output, that process just silently hangs forever.
Yeah, it just gets stuck. Provisioning via static keys completely circumvents the need for a graphical interface.
And the documentation also advises mapping the claw's initial communication channel to a Telegram integration, since it's the easiest channel to start with.
Which is wild when you think about it.
The juxtaposition is totally wild. You are interfacing with this autonomous agent running on an isolated circuit board in a closet somewhere through a standard Telegram chat interface.
It's very cyberpunk.
It really is.
Yeah.
But once that communication is established and the Openclaw dashboard is running locally over the SSH tunnel, Shish notes a major pivot in the project.
Right. The objective shifts from just making it work to making it resilient.
Here's where it gets really interesting. Because resilience is the core mandate of a claw.
Exactly. If the architectural philosophy is continuous observation, then any hardware degradation or memory leak completely undermines the entire system.
Right, out on the edge, outside a controlled data center, endurance requires ruthless optimization.
And the Openclaw documentation breaks this optimization down methodically, starting with the physical storage medium.
Yeah, they explicitly warn against relying on standard microSD cards.
Which makes sense. A persistent intelligence layer is constantly reading sensor data, writing logs, caching state.
And the physics of flash memory make SD cards highly vulnerable to write amplification, right?
Oh, absolutely. The continuous read-write cycles of an always-on Node.js application will rapidly exhaust the write endurance of a standard SD card.
Leading to catastrophic sector failure and data corruption.
Yeah, it'll just die on you. That's why booting from a USB solid-state drive is so important. It drastically increases the I/O throughput and ensures the long-term integrity of the file system.
But storage is only half the battle.
Yeah.
Managing that 2 gigabytes of RAM is the other.
Right, Shish had to ensure the event loops wouldn't crash during a memory spike.
Which meant allocating that swap space we mentioned earlier. You can
Yeah.
check the swap activity with free H, right?
Yep, free H is the command. But beyond just adding virtual memory, building for the edge means actively shedding vestigial processes.
Like trimming the fat.
Exactly. The documentation instructs developers to hunt down and disable default services like CUPS, Bluetooth, and the Avahi daemon.
Because every background daemon running on a constrained Linux kernel consumes precious CPU cycles and memory overhead.
Right. And a headless AI gateway has absolutely zero use for the CPS printing system.
Or local MDNS discovery protocols.
Exactly. By terminating those processes, you ensure that the system scheduler isn't preempting the claw's continuous observation loops just to pull a non-existent network printer.
You are stripping the system down to its bare essential sensory functions.
That's exactly it.
And speaking of sensory functions, ensuring those sensors stay awake requires overriding default power management, specifically for the network interface.
Because if the Pi drops its Wi-Fi connection, the gateway is severed from the cloud inference engine.
And the claw effectively goes brain dead.
Right. Modern operating systems aggressively manage power, They frequently put network interfaces into low power states during idle periods.
But a claw is never truly idle. It is persistently observing.
Yeah, so you have to disable Wi-Fi power management natively. The command is sudo iconfig while_0 power off.
And that ensures the wireless chip remains constantly energized.
Right, maintaining the persistent socket connections required for immediate API routing.
The documentation also highlights a critical troubleshooting metric for physical endurance, which is thermal management.
Right. The Pi 5 runs notoriously hot under load.
Yeah. So Shish used the VGen-CMD get throttled utility to monitor the silicon.
Which is super important because thermal throttling is a silent killer of asynchronous loops.
Right. When the CPU hits its thermal ceiling, it aggressively downclocks to prevent physical damage.
And for a normal reactive script, that simply means the output is delayed by a few milliseconds. Nobody notices.
But for a claw managing real-time observation, dropped clock cycles lead to timeout errors on API calls.
And dropped telemetry data.
Yeah. Monitoring that thermal state ensures the hardware isn't quietly suffocating the software.
And finally, there is the architecture layer itself. Shish points out the infamous exec format error.
Oh, yeah. That happens when you pull a binary or a new skill from a repository to add to your claw.
You have to verify it is compiled for the ARM64 architecture or ARCH64.
Right. Pulling a standard by 86 package designed for a desktop will just instantly fail.
It just won't run. When you synthesize all of these requirements, the SSD storage, swap allocation, process pruning, thermal monitoring, and architecture-specific binaries, it reveals a very distinct engineering methodology.
Yeah, you aren't just writing a script anymore. You are architecting for physical endurance.
It is highly analogous to developing software for an embedded satellite system, honestly. Uptime and resource management are paramount.
So what does this all mean? We followed Shish's journey from a conceptual shift moving from reactive chatbots to persistent, continuously observing claws, all the way down to the bare metal. We saw the deployment of a Pi 5 gateway, the circumvention of setup friction using the Pi imager, and the complex Linux service management aided by an AI copilot.
And crucially, we explored the transformation of that localized hardware into a resilient edge device.
Right. Shedding unnecessary daemons, mitigating thermal limits, and securing the storage medium to guarantee continuous operation.
Shisha's deployment proves that an intelligence layer can exist outside of a data center. It can be embedded securely and silently in our immediate physical environment.
It represents a fundamental transition.
Right.
We're moving from a world where we command our technology to execute a task to a world where our technology continuously shares our physical context and acts upon it autonomously.
This raises an important question for you to consider, though.
What's that?
Well, as developers deploy these persistent claws onto localized hardware tucked away in utility closets, warehouse shelves, and living rooms, we are going to see a rapid proliferation of edge-based autonomous agents.
Oh, well, for sure.
So at what point do these isolated claws begin detecting and interacting with each other?
Oh, wow.
Yep. We may soon find ourselves surrounded by a localized machine-to-machine ecology where our autonomous colleagues are quietly negotiating, sharing state, and optimizing our environments entirely without our intervention or our awareness.